And I then think of the infinite paths starting at this vertex and going down to infinity, and I label each infinite path with either a 0 or 1, depending on which way it goes. And in that way, this graph that I've written up here encapsulates the infinite product of zeros and ones. And what the odometer does is, well, I can order these paths by looking at the first point where they're different, if I have two paths, and then seeing whether that's a 0 or 1. And then if they're less than, if path A has got a 0 at the first point where they differ, and path B's got a 1, then I say that path A is less than path B. And then the odometer can be understood as passing from a path to the next path up in that order. So, unfortunately, Hamachi and I couldn't describe the measures on a system as simple as that. So what you have to do is instead, you have to put a finite number of dots at, well, maybe we'll start with 1 at the top, finite number of dots at each point, really as many as you like, and then join them with a finite number of edges, possibly multiple edges. And you continue like this. So this is a Bratteli-Virchik system. So what it has is it has vertices Vn, and it has edges En with source in Vn minus 1 and range in Vn. So these edges are called E1 edges, and they go from V0 up to V1. And then I need to do something about the ordering, so we need an order on all edges So if I look at this point here, that has 3 points, 3 edges arriving. I would need to order them in some way. Maybe I would put 0, 1, 2 on those 3 edges coming in. So with this structure, I can mimic exactly what happened in the 2-point case. There's a natural, so we can have x equals all paths. And, well, that's called the Virchik map. That's what Virchik contributed. Where you pass from each path to its immediate successor in this order induced by these. And so that gives you a complete analog of the odometer, but with more complicated combinatorics, obviously. A nice way of thinking about a Bratteli-Virchik system is, let me write just one dot, and then I'll write the same number of edges. There are 6 edges. Here there are 1, 2, 3, 4. Oh, I wrote 6 there again. So I can think of the set of all infinite paths here as a subset of the infinite paths of a full odometer like that, where certain paths are not allowed. So, for example, a path that joins this edge to that edge over there would not be allowed. So it's like crossing out some of the paths from this. It's like a closed subset. It's an infinite intersection of cylinders. It's a closed subset of this. And so I can try to imagine that the odometer action here might become the Virchik map over there when I think of it as an induced transformation in the sense of ergodic theory. There are questions about whether I can put an order here which is compatible and gives me the Virchik map there as an induced transformation. So what Hamachi and I showed is that our models are all Brightly-Verschick diagrams with the Markov odometer, and actually you can put a compatible order here so that you can think of the Brightly-Verschick system as an induced system in the sense of ergodic theory that I've been talking about over there. So I'm doing pretty well now. I've described to you what a Brightly-Verschick system is. I haven't described Markov measures. I've described a Markov odometer. Well, that's the Markov map there. No, I'm going to describe the measure next. I'm crossing off the things I've described, and I haven't yet crossed off what the measure is. That's my next step, to describe what the measures look like. And I've described what induced transformation, but I still haven't described to you what the Markov measure is. That's the whole point of the theorem, really, because in Dye's theorem there was no description of what the measure could look like, and now I can give you a description of what the measure can look like. Unfortunately, not exactly on an odometer, but close to an odometer. Well, so to describe a Markov measure, it's actually a kind of diffusion measure. So at each point here, I need to describe, imagine a flow going down, I need to describe the weight of each of these edges here. And then I can imagine diffusing down along the measure with certain weights telling me when I'm at a certain point what the probability of going along each of those edges is. So that's the simple idea of a Markov measure. And while the order is on the set of all vertices arriving at a point, the weights are on the set of all vertices leaving a point. So it's just the PNVs if and only the source of that edge is equal to this vertex V, so it has to start from. And secondly, there's a kind of normalization condition, the sum over the set of all edges such that the source of E is equal to edges in En, such that the source of E is equal to V of P N V E is equal to 1. So that's sufficient to allow me to define a measure on this thing, which I can think of as the probability of starting here, going to there, and then going to the next of these edges. And so if I have one of these things equipped with a Markov measure, that's what I call a Markov odometer. And now I think in the interest of time, I'm not going to quite describe to you what uniquely ergodic as a G measure is, but I think it's fairly clear. If I take one of these, well, no, maybe I should write down first what is the measure of an infinite sequence. So this is supposed to be, AI is supposed to be an edge. With the range of AI equal to the source of AI plus 1. Then I'll define mu of that to be equal to P1 of SE. Let me do it, yeah, SA1. A1 P2 of source of E2, E2. And then mu composed T, dmu composed T dmu. So it's a ratio of some of these p's divided by other of those p's, just like I wrote down for the Rees products before. And in fact, what you can do is you can then define maybe I'll just write, yeah. So this is I can define something like a, I've factored out all the first coordinates here. You can factor out, supposing you pick your favorite edge here, or the vertex here, you can factor out all the paths that get to that vertex there, all the paths that get to the vertex there. You can average over all of them, and that gives you a mu n exactly the same as we had back in the Rees product case. And I can define a G measure to be, oh look, I've got to be something that satisfies that, and ergodicity given those functions of G. And Hamachi and I showed that you can actually set up your orbit equivalence so that you get uniquely ergodic measures. If there is a unique G measure, it's not orbit. It's So I think we were quite happy when we proved this theorem because it was a generalization of Dye's theorem where you actually have a very clear working model for what the orbit equivalence class looks like. That's a Bratteli-Virchow system with one of these Markov measures on it. You can start calculating with what happens to the coordinate transformations. You know it's uniquely ergodic. However, nothing is ever completely satisfactory. And you would like to actually see the different 3-0 orbit equivalence classes inside it. That's not so clear. And the other thing is that the number of edges here, we had very little control over how quickly the edges could grow. And so we gave an example of a 3-0 system which was not orbit equivalent to any product measure. So that's an interesting question. All the von Neumann examples were just infinite product measures. There's an interesting question about whether you can find one that is not orbit equivalent to any product measure. And the answer is yes, there are. You can find examples of those. But we gave one that was a Markov odometer, but not a product measure. So I'd like, in the remaining few minutes, to tell you a little bit about the critical dimension, which is something that I and my students have been working on recently in an attempt to say more about these various orbit equivalence classes and the measures that lie on them. So let's start with our usual xb mu t, non-singular dynamical system. So the idea is, what can you say about the rate of growth can I say that equals order of n to the alpha? In the measure preserving case, these are all 1. This adds up to n, so it's order of n to the 1. But what about in the non-measure preserving case? It's quite an interesting question to say how quickly can, and you can think about this as I'm going around an orbit and I'm taking consecutive points here, and I'm not counting 1, 2, 3, I'm counting, there's x. I need to count this not as 1, but as the weight that I get when I look at what the Radon-Nikodym derivative is doing. So that gives me a kind of weighted sum around an orbit. And there are lots of ergodic theorems like Rudolph's restricted orbit equivalence, where you count the number of points on an orbit. But in the non-singular case, you need to count them with this weighting on them. So from that, we got this idea. So let me divide by n to the alpha. Look at the set of all x such that maybe I'll write the lim inf of that is greater than 0. Well, that x, maybe I'll divide it by x alpha dashed. And if I replace x with tx there, then there are properties of the Radon derivative which ensure that this is omega I of x over omega I of tx times the Radon derivative omega 1. So actually, you can therefore see that if I replace x here with tx, then tx is also in x alpha dashed. And therefore, the measure of x alpha dashed is equal to 0 or 1. If we look at the Horevich-Ergodic theorem, implies that this thing here diverges so in other words, if I put alpha dashed equal to 0, mu of x0 equals 1. On the other hand, if I put alpha equal to 1, then it always converges, which I'm not going to show you, but mu of x1. And that means that somewhere in between 0 and 1 there will exist an alpha where the measure changes from 0 to 1. And that we'll call the lower critical dimension. Mm-hmm. Yes, it must be ergodic for this argument to work. And so alpha is equal to the, I think it must be the max, the sup over alpha dashed, so that mu of alpha dashed x alpha dashed equals 1 is the lower critical dimension. And then I can put lim sup there, and inf here and beta there. And therefore I get these two numbers, alpha and beta. They can be equal or they might not be equal. But they're clearly invariants of a metric isomorphism. Well, clearly it's not very hard to see that they are. But they're not invariants of orbit equivalence. Let me put equals there. That's kind of interesting when alpha equals beta. Now, we were very surprised when Jan Mortis was writing her PhD in 96 or 7 or something like that. We were very surprised when we decided we should calculate this for infinite product cases. Let's take an infinite product measure on a finite infinite product. What can you calculate what alpha and beta is? So well, it's a bit boring to leave it as 2 all the time, so I'll let Li be some sequence of numbers, finite numbers. Take a probability measure on each of those spaces. Then alpha is equal to the lim inf. This is what she proved, 1 over Sn. That's the number. That's L1 times L2 up to Ln. That's the number of edges up to the nth one. So it turned out that alpha actually equals the average entropy up to the nth point. We were very surprised that it equaled the entropy, but it does. So you take the entropy of each coordinate measure, that's the minus mu, minus pi log pi that we were talking about the other day. You take the Cesaro mean of that up to the nth thing, take the lim inf of that, and that's beta, that's alpha, and beta is the lim sup. So this was what we called it, the average coordinate entropy.
X is equal to product.
Yeah, so x is equal to the infinite product of, so ZLI I think of as the integers 0, 1 up to Li minus 1. So it's a point with Li spaces, points on, a space with Li points on it. And this is a probability, these are probability measures on each of those points. Then you can actually work out the alpha and the beta for those. Sorry? No, the measure's not invariant here. It's a quasi-invariant measure. That's the odometer acting on an infinite product space. Yeah, so I should have said T equals the odometer. Yeah, you're quite right. So work out the entropy of each individual coordinate and then take the average of that divided by the number of coordinates. And then take the lim inf and the lim sup, and that gives you the two critical dimensions. Well, so in fact, we've now extended this result to any Brightly-Verschick system as well. Well, I guess there was me, there was Mortis, there was Rika Hagihara, who was a Japanese girl who left Japan and went to work with Jane Hawkins at North Carolina. And most lately there's been my student Daniel Mansfield, who's just finished his PhD. I think there was an important thing missing here, and that is that there had to be an uniform upper bound on all the edges, on the number of edges. And Daniel has recently made that actually the edges, if the edges grow sub-exponentially, that's sufficient to have this same thing, and he's extended it to Markov odometers on Brightly-Verschick systems. I think I started at 11:30, and I therefore have 3 more minutes, in which case I'd like to tell you another result, which is a little bit like the Ornstein result. It's very easy, now that we know that this is the way to calculate, it's very easy to find a type 3 lambda system and then put a few other, instead of lambda 1 over 1 plus lambda on every coordinate, you can put some half-halves in the middle of it and have it remain 3 lambda, and you can change the limit of the average coordinate entropy quite a lot. So you can actually make the average coordinate entry be any number for a 3 lambda between 0 and 1. So don't go imagining that this is an invariant of orbit equivalence. But there ought to be some map, some kind of map that preserves these, preserves the critical dimension. And, well, we've called it Hurewicz equivalence. So x b mu t, y c nu s